So before we get into today's lecture, I want to just look at homework set number one with you guys very briefly here. Uh, Trevor, I will probably wind up posting both the notes and the videos. Definitely the videos. The notes is mainly if I remember to actually do it, like to save them. So for this first problem, I think relatively straightforward, except for part C, where you're asked to determine the Thevenin resistance seen between the terminals by calculating the equivalent resistance. So I'm specifically telling you, you can't just use VTH over I Norton to get RTH. I want you to find the equivalent resistance. This particular network does not have an easy way to find the equivalent resistance using the resistor combination techniques that you all are familiar with. So I give you a hint here, and this hint is actually just telling you what it is that you need to do. You either need to perform a delta Y conversion or delta Y transformation on some part of this network, which I understand that you guys do not know how to do. I'm intentionally telling you, hey, look it up and figure it out. Or you can do something that you already know how to do, which would be to use the test source method, because that would allow you to do node-aware mesh or something like that and just find the ratio of the test source to the other quantity. Okay. So problem one, part C is relatively tricky, but there's a very easy way for you to check whether or not you did it right. For what it's worth, we're going to wind up using delta Y transformations a whole hell of a lot once we get to the three-phase power section of this class. So I'm trying to introduce that to you relatively early. Problem two is fairly straightforward, or at least I feel it is. Problem three is fairly straightforward. It's just testing your ability to use the test source method. Problem four looks a little tricky, but I want to talk about this one very briefly. During the transient condition, this switch is closed, which means this branch right here looks like an open circuit or a short circuit.
This looks like a short.
It looks like a short circuit. Okay, so you have this RL branch in parallel with a short, and you have this RL branch over here on the right in parallel with a short. Because they are in parallel with a short circuit, they are going to behave as independent RL circuits, which is why there are two time constants listed and all of that kind of good stuff. So I just wanted to make you aware of that. This isn't supposed to be something that you've never done before. Okay. We'll handle what happens when you don't have independent RL circuits in maybe 2 to 3 weeks. Okay. And then homework set number or problem five is just another transient analysis problem, except that this one contains a dependent source. So essentially, you're going to wind up having to use the test source method in order to calculate the equivalent resistance of the network that contains that dependent source, seen from the perspective of that half Henry inductance in order to figure out what your time constant is. Okay, so like I said, taking what we did in circuits one and just going a little step further. If you need more clarification, by all means, please email me, shoot me a text or whatever over the weekend, and I'd be happy to help you out. I did provide you with the answers to all of these questions. I believe all of those answers are correct. Okay. Um, if I have a homework set like homework number two, which is already uploaded, where I don't provide you the answers, that is usually intentional because it means that I think if I just give you the answers, there's not enough work for you to do, kind of thing. Okay. When I do provide you the answers, most of you are familiar enough with me to know that I am a jackass and I make mistakes very regularly. So take my correct answers with a grain of salt. If you get something different and you think you're right, let's talk about it. There is a non-zero chance that I have just made some asinine mistake because I was in a hurry or overlooked something. Okay. So just want to throw that out there. Take my correct answers with a grain of salt because I'm me, which means mistakes are going to happen. All right, let's get into today's lecture. So this is going to be, let me see what chat. Oh, that's from, and okay, that's nothing to do with this class. All right. So today we are going to be talking about an introduction to amplifiers. Okay. So in circuits one, we talked about op amp circuits relatively briefly. I don't think this is a big ask, but I would like for you guys to just completely forget any and everything that we covered about op amps in circuits one, because we're going to go into a much deeper dive here in circuits two. In circuits one, we were only concerned with negative feedback amplifiers and only ideal op amps as well. Here, we're going to look at things in a much more practical standpoint so that we can show what we can do, how we should design things, and all of that kind of good stuff. Okay. So before I even introduce op amps in this class, I want us to get an understanding of what the role of an amplifier in general is. Okay. So one of the most basic signal processing operations that we can do is the amplification of a signal, where we simply just take some input signal and make its magnitude larger. So I'm going to start with a very simple diagram here. So let's say that I have some input signal x of t, like so. Okay. Where, for simplicity's sake, I'm just going to make this a simple sinusoid. So I've got a sinusoidal signal like so, and I'm going to feed this signal x of t into an amplifier. Okay. So I'm going to choose to represent this in what's called a signal flow diagram for right now. We'll get into the circuit side of things in a bit. So the symbol for an amplifier is just a triangle, exactly like we use for an op amp, where x of t, my input signal, is applied here, and y of t, my output signal, is taken here. And this amplifier provides some amount of gain A. Okay, so I'm just going to kind of annotate this really quickly. So this is my input signal. This is my output signal. And this guy in the middle is my amplifier. Okay. So what's happening here is my input signal is fed into my amplifier. And that input signal could be a current, a voltage, or a power signal. And then it's going to get acted on by that amplifier, um, which in a mathematical sense just means we're going to take the amplifier's gain A, which is just some scaling factor, and we're going to multiply that scaling factor by our input signal to get our output signal. So y of t in this case is just going to be A, our gain, multiplied by x of t. And so what we should expect to see for this system is an output signal that looks something like this, right? So here's y of t as a function of time, assuming that our gain is greater than 1. We should see that our output signal is just the exact same thing as our input signal, but larger. Okay, that's the ultimate goal of an amplifier. Okay. So amplifiers are used in a whole lot of different applications that we interact with in our everyday lives. So I'm going to draw a kind of block diagram representation of a radio. like the one that we might have in our cars or as part of our phones, things like that. So on the input side of things, we might have an antenna. So that's what this symbol right here is. And I will annotate this as well in a moment. And the signal from our antenna gets fed into a radio frequency filter. So this is the block diagram symbol for our filter. That signal is going to be fed into an amplifier. So this is our radio frequency amplifier, and then this signal is then fed into a mixer, which combines our radio frequency signal with a clock signal or an oscillator signal, usually set at some specific intermediate frequency. Okay. The output of this mixer is then fed into yet another filter, amplified again, fed into a demodulator, which is separating the intermediate signal and the message signal. Amplified a third time before the signal finally has enough power to drive a speaker. So let me go through and annotate this thing really quickly. So over here on the input side, we have our antenna. Then we have our radio frequency. So that's just our RF filter. Then we have our RF amplifier. This is, again, our mixer, our local oscillator. This is our intermediate frequency filter. This is our intermediate frequency amplifier. Our demodulator. Our audio amplifier. And lastly, our speaker. So why are so many different amplifiers and filter stages needed for this? Okay. So let me ask you guys a question. What is the frequency or frequency range associated with human speech? Does anybody know? So the lowest thing that we can hear is on the order of 15 hertz. And the highest frequency that we can hear is on the order of 20 kilohertz. Okay, so all of human speech, so the 20 kilohertz is like symbols and stuff like that, like the very high frequency stuff. So human speech usually tapers off somewhere in the ballpark of 4.5 to 6 kilohertz. But for all of the stuff that we can hear, like music, because we listen to music and things on the radio, excuse me, we need to be able to filter out things above, let's say 20 kilohertz, because that's beyond the range of our hearing. Okay. Now, what frequency do radios, like radio stations and stuff like that, broadcast at? Or what is the frequency associated with, telephony and things? Anybody have any ideas? So it kind of depends. So if we're listening to an AM radio station, which practically none of us are, and you're listening to like sports talk or something like that, that's usually on the order of, so let's say like 1500 kilohertz or something like that, in that ballpark. If we're listening to FM radio stations, that's about 100 megahertz. So the FM frequency band starts at, I believe, 85 megahertz and it ends at, I think, 107 megahertz or somewhere around there. we're listening to satellite radio stuff, that is on the order of gigahertz. If we're listening to things over like a Bluetooth connection, that's also gigahertz, all of that kind of good stuff. So essentially, the frequencies that are used to transmit information, like sound and stuff like that, like a song or a message or anything, is way, way higher in frequency than what we can actually hear, right? So we take our antenna. Anybody have any idea about the size of the signal that might be picked up by your antenna? Okay. So have you guys had Physics 202 yet? Most of you, or some of you have had Physics 202, some of you have not. So the antenna is just picking up an electromagnetic wave that's carrying all of this information, okay? Electromagnetic waves strength decays pretty rapidly the further away that you get from your signal source. So in most cases, unless you're very, very close by to like a cell phone tower, the radio station, or something like that, the signal that you're picking up by your antenna is millivolts to microvolts. It's very, very small, okay? So we filter out the stuff we don't want from that very, very small signal. Then we boost it with this RF amplifier. We run it through this oscillator so that it has a specific reference frequency that we then filter out. So we're trying to just extract our message signal from that. Run it through this amplifier again because we need more signal power. Run it through the demodulator so that we only have the message that we're trying to get. And then we run it into a power amplifier so that it's actually got enough voltage and current to be able to drive a speaker. Because a speaker has physical mass that we need to be able to move with this electrical signal through electromagnetic induction, which you guys will learn all about later in your classes. But essentially, if we don't give this signal enough power to literally move the speaker cone, we wouldn't hear anything, okay? So that's why we have so many intermediate stages here. We have some voltage amplifiers, we have some current amplifiers, we have some power amplifiers, because the ultimate goal is to take that signal, whether it's, Enter Sandman by Metallica or some classical musical piece, and we need to be able to transmit that or convert that electrical signal into an audio signal, which means we have to physically move the cone of a speaker to make that happen, okay? So that's what amplifiers are doing in this system, okay? So how amplifiers are able to do that is because they are what are called active systems, okay? So an active system simply means that they require external power, okay? So resistors, capacitors, and inductors, those are all passive components because they're just going to do what they're going to do. An amplifier requires external power so that we can boost our signal power. We need extra energy to come from somewhere else in order to provide that boost or provide that amplification. So a slightly better representation of our amplifier as a block diagram component would actually look more like this, okay? So here's my amplifier representation, still just my triangle. Here's my input signal, X of t, my gain, A, my output signal, Y of t, which in this case is just going to be A times X of t. But I'm going to modify this slightly and say that up here, I'm going to have another terminal. And I'm going to call this VCC plus. And down here, I'm going to have another terminal, which I'm going to call VCC minus. VCC plus is my positive power supply voltage, or so positive supply voltage. And VCC minus is my negative supply voltage. Now, some amplifiers are what are called single supply amplifiers, and that just means that the negative supply voltage is ground. So we just tie that directly to ground, and we don't have to worry about generating two different voltages in order to power our system, okay? Now, these supply voltages are actually very important because the amount of signal that can be supplied on the output of our amplifier is actually limited by these supply voltages. So that output signal, if it's a voltage, can never be greater than the positive supply voltage, and it can never be more negative than the negative supply voltage. So those give us our window of acceptable output voltages. And we'll talk about that more when we deal with op amps and distortion that can happen if we ever have too much gain in our system, okay? So these external supplies are providing the extra power that needs to be delivered to the load that our input signal isn't capable of doing, as well as any power that's consumed by the internal circuitry of the amplifiers. And as I mentioned a moment ago, the size of these supply voltages limits the output power that can be produced by the amplifier. Okay. So now let's talk briefly about amplifier parameters and models. So the internal circuitry of an amplifier can be extremely complex. Probably the most simple amplifier is a single transistor amplifier, which will have a single transistor and then anywhere between 3 to up to maybe 5 or 6 different resistors that are used in various biasing configurations, okay? And then your more complex amplifiers, like the internal circuitry inside of an op amp, can be tens or hundreds of transistors, tens or hundreds of resistors, capacitors, inductors, diodes, and all of that kind of good stuff. So an amplifier as a collection of components can be incredibly difficult to analyze. But luckily for us, we don't really have to understand how they work internally to get an idea of how they work as a single device overall, okay? So generally speaking, the performance of an amplifier can be quantified by just 3 different things, okay? The first of which is the gain of the amplifier, then the input resistance of the amplifier, and then the output resistance of the amplifier. So I'm going to define the gain of an amplifier as simply A is equal to the ratio of our output signal over our input signal. Or using the quantities from our little block diagram representation, this would be y of t over x of t. So this is our fundamental definition for gain. The type of gain that's provided by an amplifier depends on the type of input signal that the amplifier acts on, as well as the output signal that the amplifier produces. So that means that there are multiple different types of amplifiers that can have multiple different types of gains. So we're going to kind of walk our way through those really quickly. So the first amplifier that I'm going to introduce is the voltage amplifier. And I'm going to draw a simple circuit here. So here's my amplifier. I'm going to define this gain as A subscript V, and I'll talk about what that means in a moment. So over here on the left-hand side is going to be the input signal for our amplifier, Vn of t. Over here on the right-hand side is going to be our output signal, V out of T. And then to fully show what's going on, I'm also going to include a signal source over here on the left, as well as a load over here on the right. Okay. So let me just annotate this really quickly. Signal source over here, load over here. So hopefully pretty easily, we can see that in this case, our input signal to the amplifier is a voltage, Vn of t. Our output signal is also a voltage, V out of t. And so from this, our gain is defined as A subscript V, which just stands for voltage gain, is V out over V in, and it will have units of volts per volt. The overwhelming majority of amplifiers that we're going to deal with in this class and the ones that you will utilize throughout your engineering experience will probably be voltage amplifiers, okay? So the next type of amplifier that I'm going to briefly discuss is the current amplifier. Okay? So I think I've got enough space to do it here. So starting off with my same basic picture. Here's my amplifier. I'm going to have a current gain of A sub I. And then measured between these terminals. Actually, I'm going to leave those blank since this is a current amplifier. Oh, I'm drawing this shittily, sorry. So here's my amplifier circuit. I'm going to have some input current signal, In of t here. I'm going to have some output current signal, I out of t here. That input signal is going to be generated by a signal source, yet again. And the output signal is going to, once again, drive some sort of load. Like so. I'm not going to bother writing down signal source and load again. Those are just going to be carried through all of them. Okay. So in this particular case, our input signal is a current. Our output signal is also a current. And so our gain is simply a current gain. Where I'm going to say that A sub I is just the ratio of I out over I in. So it will be measured in amps per amps. And let me just note that this is indeed current gain. And now we're just going to start mixing and matching voltages and currents, right? So the next one that we'll talk about is a transconductance amplifier. And in a transconductance amplifier, our input signal is a voltage and our output signal is a current. So here is Vn of t, I out of t. And once again, I'm going to attach my signal source and the load I'm trying to drive. So this is going to be a gain of A sub G. So we'll have our input signal is Vn. Our output signal is I out. And our gain, A sub G, is going to be simply I out divided by In. So this will, excuse me, I out divided by Vn. My apologies. So this will have units of amps per volt. And this will be our transconductance gain. And then lastly, we have our trans resistance or trans impedance amplifier. Those two terms are used interchangeably. I'm just going to call this guy a trans resistance amplifier. In a trans resistance amplifier, our input signal is a current and our output signal is a voltage. So here is my input current signal. Here is my output voltage signal. And I'm going to call this gain my trans resistance gain A sub R. Okay. And once again, I'm going to connect my signal source and my load. Like so. So my input signal was a current. Output signal was a voltage. And my gain is the ratio of those two quantities. A sub R is equal to V out over I in, which obviously has units of volts per amp, where this guy A sub R is my trans resistance gain. For what it's worth, it might not be obvious yet, but it will be in probably 5 minutes. These different types of amplifiers are the reason why we have different types of dependent sources that we have to talk about in circuits one, right? So each one of these has an associated type of dependent source. So the voltage amplifier is going to be represented by a voltage controlled voltage source. The current amplifier is going to be represented by a current controlled current source. The transconductance amplifier is going to be represented by a voltage controlled current source, and the transresistance amplifier will be a current controlled voltage source. And we'll see all of that here in a couple of minutes. So, yes.
Does the amplifier determine the signal, or does the signal determine the amplifier? Like, are you
The
getting-
signal determines the amplifier.
Okay.
So I can take an op amp, which is usually considered to be a voltage amplifier, but if my input signal is a current, it is now a transimpedance amplifier. So it's the signals that we're measuring, the signal that we're applying at the input and the signal that we're measuring at the output that is going to determine the type of amplifier that it is behaving as. All of these things could be implemented by the exact same amplifier. It's just what we're trying to do with it. Okay, so yes. So technically, yes. And we'll talk about that in a couple of minutes when we start trying to chain these things together and all of that kind of good stuff. So the goal of an amplifier is to make a signal stronger, but if we don't pay attention to some very specific things having to do with the input resistance and the output resistance of our amplifier, we can very easily accidentally make our signal weaker than we wanted to, which is literally the thing that I'm about to talk about. So great question. Yeah. So I think we've done I think I've talked enough about the concept of gain, just the ratio of output signal to input signal, how that's going to be different things depending on what signals that we are introducing to the system and what signals that we're measuring at the end of the system. Now let's talk about input resistance. So the input resistance of an amplifier, that's not the right color. Is related to how well the amplifier preserves the input signal. So the way that the input resistance of an amplifier is determined is always the same thing, okay? So I'm just going to take a generic amplifier here. Doesn't matter what kind it is. So this guy right here, without putting any additional information, could be literally any of the 4 types of amplifiers that I've discussed previously. And what I'm going to do is I'm going to excite this amplifier with some sort of source. Could be a DC source, could be an AC source, doesn't particularly matter. And what I'm going to do is I'm going to measure the voltage drop across the terminals of the amplifier and the current flowing into the amplifier, like so. I have to do this with the output terminals open circuited. So I'm just going to put a note here. The reason why the amplifier's output terminals must be open circuited is because I don't want to take into account any effects that the connected load might have. So I'm just trying to quantify amplifier behavior right now, not system behavior. When we talk about system output resistance in a couple of days, we'll connect a load there. Okay. So our input resistance for our amplifier, Rn, is literally just going to be the ratio of the voltage we measure across the input terminals divided by the current flowing into the input terminals of the amplifier, because that's just Ohm's law. Voltage over current is the resistance. So this is just a test way to find the resistance looking into the input terminal of the amplifier. So it's the input resistance of the amplifier. Okay. So typically speaking, and your first homework assignment is literally about this, or sorry, not your first homework assignment. The first problem of your second homework assignment is about this. So typically speaking, when the input signal is a voltage waveform, we want the amplifier to have a large input resistance, and we'll see why that is when we work a couple of examples. And whenever the input signal is a current waveform, we want the amplifier to have a very small input resistance. The flip side of things is the output resistance of an amplifier. Okay. So the output resistance of an amplifier is related to how well the amplifier can drive a load. So in order to measure the output resistance of an amplifier, I'm going to draw a little schematic representation here really quickly. Starting again with just our basic amplifier circuit, doesn't matter if it's voltage, current, transresistance, or transconductance, it's all measured the same way. And what I'm going to do is I'm going to excite the output terminals with some type of source. So I'm going to measure the voltage drop across the output terminals, Vx, as well as the current flowing into the output terminals, Ix, while my input terminals are short circuited. Okay. And I'm going to put a little note over here. To measure output resistance, the amplifier's input terminals must be short-circuited. So the reason for this is that all real signal sources will have some internal resistance, right? So we're going to represent real signal sources in this class using practical voltage sources and practical current sources, which we talked about back in circuits 1. Okay. So we don't want to accidentally include the internal resistance of those sources when we are trying to figure out what our amplifier parameters are, because those are going to change depending on what we use to generate our signal. So we just short those input terminals out to make sure that the resistance on the input side of the system is literally just 0 so that it doesn't influence our measurement. Okay. And once again, the resistance that we're going to find here is just the ratio of that voltage Vx to that current Ix. So typically speaking, when the output signal is a voltage waveform, we want the amplifier to have a small output resistance, so exactly opposite that of the input resistance. And when the output signal is a current waveform, we want the amplifier to have a large output resistance. Again, exactly opposite what we saw for the input resistance. So if we know these 3 parameters, the gain, the input resistance, and the output resistance, that means that we can replace any amplifier circuit, no matter how simple or complicated it is, with a very simplified practical model. And I'm going to introduce you guys to those practical models here. Okay. So over here on the top left, I'm going to do the voltage amplifier model. So anytime that we have a voltage amplifier where gain, input resistance, and output resistance are known quantities, we can just replace it with this simple circuit. Here is our input resistance. These are the terminals across which we apply our input voltage. Because this is a voltage amplifier, we are going to use a voltage-controlled voltage source to provide our gain in our model. And then here is the output resistance. And I'm just going to tie all of this together like so. Okay. Where this is our output voltage. So before I move on from here and show you some of the other models, we mentioned a couple of moments ago, or I mentioned a couple of moments ago, that whenever we have a voltage signal as our input, typically speaking, we want our input resistance to be as large as possible. So let's talk about that really quickly. I'm going to wind up erasing this in a moment, so you guys don't need to write this down. Just think about it for a moment, okay? So let's say that I have some practical voltage source over here connected on the source side of things, where this is V sig and this is R sig. What I have on the input side of this amplifier is a voltage divider, right? So V in, the signal that's applied to the amplifier, is just going to be V sig times Rn over R sig plus Rn. So the larger Rn is, or the greater Rn is compared to R sig, the input signal that's being applied to the amplifier terminals looks closer and closer to actually V sig, so that the internal resistance of the signal source doesn't matter, okay? And on the outside, output side of things, here's some load resistance, right? I literally just have another voltage divider circuit, okay? So if I want my output signal to just be a scaled version of my input signal, then I want R out to be as small as possible so that there's not a voltage drop across that little resistor, so that all of the output voltage gets applied to my load. So that's why we want the input signal to be as large, the input resistance to be as large as possible, and the output resistance to be as small as possible. It literally preserves the signal all the way through its signal path, right? So to answer your question from earlier, if I have a voltage amplifier with a very low input resistance, I'm going to kill most of my input signal at that stage, right? Or if I have a voltage amplifier with a very high output resistance, I'm going to just consume a whole bunch of excess power in that output resistance that isn't going to get delivered to my load.
Is that low and high relative to?
The input signal resistance and the output load resistance. So we are gonna kind of talk about, I don't want to say impedance matching because that has a very specific meaning, but we're going to work some examples where we're going to have multiple amplifiers that we need to cascade together in order to hit a specific design criteria. And we're going to see what the impacts of using low input resistance and high input resistance and low output resistance and high output resistance does to signal integrity and the amount of power that's delivered in our system. Okay, let me erase all of this stuff in blue now. So there's our voltage amplifier model. So over here on the right, I think I have enough room here. I'll do the current amplifier model. And it's going to be a very similar looking thing, except that I'm going to use a current controlled current source on the output side, right? So here's my input terminals. Here's Rn, and here's my input signal, In. Now I've got a current source here, AI times In of t. And because I've got a current source here on the outside, I'm going to put my output resistance in parallel. So here's I out of t. So if we imagine very briefly, and again, I'm going to wind up erasing this in a moment, so you don't need to really write it down, a case where I'm attaching let's just say a practical current source here. Right, on the input side. In this case, I want my input resistance to be as small as possible so that almost all of my input signal actually flows this way, right? So if Rn is less than Rsig, more of our input signal is preserved flowing into the amplifier. On the output side of things, here's my load resistor again, right? So I want R out to be greater so that all of the current that's provided by this dependent source flows through my load instead of branching off and flowing through that path. Okay. For our transconductance amplifier, it's just going to look like a combination of these two, where the input side is the same as the voltage amplifier and the output side is the same as the current amplifier. So something like this. where here is VN, RN, AG times VN, R out, and I out. And lastly, we have our trans resistance amplifier model. And this is going to have the same input side as a current amplifier and the same output as a voltage amplifier. So this will be IN, RN, AR times IN, R out, and lastly, B out. We draw a line under this. Let's finally get to an example. So in part A, let's say that we have a transducer. That's just something that's capable of generating an electrical signal. So a transducer which generates signals of magnitude V sig is equal to 10 millivolts and has an internal resistance of R sig is equal to 100 kiloohms. Bless you. Is connected to a 100 ohm load. As shown below. Okay. So here's my 10 millivolt input signal. Here's my 100 kilo ohm signal resistance. Here's my 100 ohm load resistance. Like so. I'm just going to label these things really quickly so that you can use this generically later if you need it, which I think you will for homework assignments and stuff, right? So here's our simple system. The transducer itself is trying to drive some load. And so I want to know what is the overall system gain. So I'm going to define a system as simply V out, which I'll define that as just the voltage drop across the load. over V sig, and how much power is delivered to the load. Okay. So before I start on part B and all of this kind of stuff, let's just figure this out. Okay. So what I'm trying to demonstrate in this particular part of this problem is the need for amplification. Okay. So this transducer might represent possibly a piezoelectric sensor, like would be used to maybe measure a person's heartbeat or something like that. Okay. So typically speaking, a piezoelectric sensor does a pretty good job of generating voltages and an absolute shit job of being able to generate current. So it isn't capable of producing a lot of power overall. It's just really good at making relatively large voltages. If any of you guys or any of your parents have a grill with an electric ignition, chances are it has a piezoelectric crystal where when you push the button, it actually deforms that crystal, which creates a large enough voltage that it actually creates a spark or a plasma. But the amount of current that it can supply, again, is absolute trash. Okay. So how would I go about finding the output voltage for this system? Voltage divider. Why not? I have a known voltage and then two resistors in series, so that seems like the laziest possible way to do it. So I'm going to do this in, I don't know, this gray color so that way I can denote that it is the solution here. So using voltage division, I can say that my output voltage V out is just going to be V sig times my load resistance divided by R sig plus my load resistance. Substituting in numbers here, that's going to look like 10 millivolts multiplied by 100 ohms over 100 kiloohms plus 100 ohms. And that's going to come out to be 9.990 microvolt. Okay. And from this, our system gain, which is just V out over V sig, is going to be 9.990 microvolts over 10 millivolts, which gives us a gain of 9.990 times 10 to the minus 4 volts per volt. And my load power is just going to be my output voltage squared divided by my load resistance. So that would be 9.990 microvolts squared over 100 ohms. Comes out to be 9.998 times 10 to the minus 13 watts. So this transducer by itself delivers practically no power to the load whatsoever. Okay. So in part B, let's see what happens. No. Did it just say that it's opening a PowerPoint? I hope not. So let's say if the transducer was connected to a voltage amplifier, which is used to drive the load. What would the overall system gain and power delivered to the load be if our amplifier's voltage gain is 1,000 volts per volt, which is a actually pretty modest voltage gain. Our input resistance were 10 kilo ohms, and our output resistance was 1 kilo ohm. So I'm going to redraw this circuit with the gain, or excuse me, not the gain, the amplifier put in between the signal source and the output load, right? So that would look something like this. So there's my source. These are the input terminals of my voltage amplifier. So this guy right here is going to be my input resistance, which I said was 10 kilo ohms. What it's worth, this one was, I think, 100 kilo ohms. This was 10 millivolts. Over here, I'm going to put the output side of my amplifier. Since it's a voltage amplifier, this is going to be a voltage controlled voltage source. My gain is 1,000, which is just 10 to the 3. So I'm just going to call this 10 to the 3 times Vn, where this is my voltage Vn, the input signal for my amplifier. Here's my output resistance of 1 kilo ohm. And lastly, over here to the right, I have my load resistance of 100 ohms, where this guy is now V out. Okay. So the analysis is a little bit more complicated, but it shouldn't be too bad because it's just two voltage dividers, right? So if I can figure out using voltage division what Vin is, I can then use voltage division on the output side of the circuit to figure out what V out is. Okay. So using voltage division, I could say that Vn is going to be V sig times Rn over R sig plus Rn, which in this case would be 10 millivolts times 10 kilo ohms over 100 kilo ohms plus 10 kilo ohms. And when I did that, I wound up getting a voltage of 909.091 microvolts. So that is significantly larger than when the amplifier wasn't there, right? Let me just scroll back up here. So I had 9.9 microvolts. Now I have 900 microvolts. So that increased my signal preservation by a factor of almost 100. Okay. On the output side of things, V out is going to be, this is just using voltage division. My voltage gain times Vn multiplied by RL over R out plus RL. So that comes out to be 10 to the 3 times 909.091 microvolts times, let's see, 100 ohms over 1 kilo ohm plus 100 ohms. And I got this to be 82.645 millivolts. So my output signal is now larger than my input signal. So that's fantastic. So I believe I've supplied a lot more power to my load. Let's see what our overall system gain is really quickly. So A system in this case, still just going to be V out over V sig. So that's going to be 82.645 millivolts divided by 10 millivolts gives me a voltage gain of 8.265. I'm rounding here. Volts per volt. And lastly, my output power, PL here, still just going to be V out squared over RL. But since my output voltage is much larger, I should see a lot more output power. 82.645 millivolts quantity squared divided by 100 ohms, which comes out to be 6.830 times 10 to the minus 5 watts. So previously we were at 10 to the minus 13 watts. Now we're at 10 to the minus 5 watts. So based on my simple math, that's a factor of 10 to the 8 difference. So that's what, 100 million times more power? So pretty damn significant, right? I want us to look at a couple of things though really quickly here. And I know that I'm almost out of time. So my amplifier's gain in this case was 1,000, right? But my system gain was only 8.265 volts. So that's actually a significant reduction in gain overall than what my amplifier is capable of providing. The reason why my system gain is so much lower than my amplifier's gain is because I still don't really have good impedance matching on the input side, right? So my input resistance for my amplifier of 10 kilo ohms is actually 10 times smaller than my signal resistance. So if I had an amplifier to where the input resistance was larger, what I would see is that my system gain would go up, okay? Because that voltage divider ratio right there, and when I'm calculating V in, would be larger, okay? So if Rn is larger, then Rn over R sig plus Rn is going to be larger as well, which means more of my input signal, or more of V sig, gets preserved as it goes to the input of the amplifier. Similarly, my output resistance of my amplifier is actually 10 times larger than my load resistance, right? So if that R out were lower, I would get a larger voltage divider ratio output side of things, which would also increase my overall system gain, okay? So choosing an amplifier that matches the parameters of the external things that you are going to connect to it makes a big difference in the overall performance of the amplifier itself. So going back to what I had mentioned earlier, when we have a voltage amplifier system, we typically want the input resistance to be as large as it can possibly be, and the output resistance to be as small as it can possibly be, because that's going to make the system gain be as close to the amplifier's gain as we can possibly get it. Okay. So this is going to be where we stop for today because literally I ran out of time to talk about other shit. So at the very beginning of our next class, we're going to talk about cascading general amplifier stages together and see what those impacts are. So right now, you guys should be okay to start working on problems 1 through 3 of homework set number 2, but problem 4 needs to wait until we cover this other stuff. Just wanted to give you a heads up.